In this video, we are going to look at these last two examples where we are going to find some absolute extrema. Let's look at this first function. So our first function is g of x is the absolute value of x plus 4, and we are on this interval from -1 to 6. Our derivative is going to be piecewise defined as being either 1 or -1. It is -1 if we have values to the left of -4, and it's +1 if we have values to the right of -4. Right at -4, that's going to be where we have the vertex of this absolute value graph. That's where the derivative would not exist. So the only critical value we have here is -4, but that is not in the interval from -1 to -6. Perfect. So if we're trying to find an absolute maximum, absolute minimum, we have no critical values. Now all we need to do is plug in our endpoints. So plug in -1, and we get 3. Plug in +1, not +1, plug in 6, the right-hand endpoint, plug in 6, and we get 10. So our absolute maximum is 6, 10, and the absolute minimum is -1, 3. Those are our absolute extrema. Great. And we have one final example that has 4 different parts. Here we have k of x equals x squared minus 2x. We're going to find an absolute extrema, so let's first find our derivative. And our derivative here, k prime of x, is 2x minus 2. And so our critical values is just going to be 1 itself. So for this first function, going from -1 to 2, we can plug in -1 into the original function. If we plug in -1, we will get an output of 3. We can plug in 1, our critical value. And when we plug in 1, we get an output of -1. And when we plug in 2, we get an output of 0. And so those are all from plugging it back into the original function. And so for this first one, on that interval, we plugged in the -1 and the 2. The absolute min, the absolute minimum, is going to occur at -1, and that has an, the absolute minimum, it occurs at +1, and had that output of -1. And the absolute max is -1, 3. Good. For the second function, second interval rather, it's a half-open interval, or half-closed interval. We are not including the value 1, but we are including the value 3. When we plug in, when we look at this, we have a maximum at 3, 3. But the minimum here does not exist. Why doesn't that minimum exist? Well, this function is going to keep getting smaller and smaller as we approach 1. And so since we're never actually reaching 1, I can always find a value that's a little bit smaller and find another value that's even smaller still. So that has an absolute maximum on that interval, but no absolute minimum. The next one, we are looking at an interval from 0 to 2. When we look at this interval from 0 to 2, then we are going to find no absolute maximum. Our minimum, we are going to find, is occurring at 1, negative 1. Okay. So as we approach 2, our function values are going to get larger and larger and larger, but we can never actually hit 2. So we have no maximum, but there is a minimum in that interval at 1 itself. And finally, when we are looking at the half-closed interval from 1 to 4 as a maximum, we find, again, our maximum here does not exist. And our minimum here is at exactly the same point. So you might want to look at a graph of those to help convince yourself that on this interval, we do have a function value that's the absolute smallest, but our largest one is the one that's closest to 4, occurs when the x value is closest to 4. And since it can always get closer and closer and closer and closer and closer to 4, there is not actually an absolute max. Now, if we would put a bracket there, if we had a closed interval, then we would be guaranteed to have a maximum and minimum. We'd be guaranteed of those if we had closed brackets, because we could actually reach those values. All right, come back for our next video when we will look at some more items that our first derivative will tell us about graphs and pictures of functions. We will see you there.